There we go. Okay, so with the natural numbers and the whole numbers, we add to that the integers. And so we have this concept that we can make all of our natural numbers negative as well. So an integer, when I'm talking about integers, I'm talking about numbers like 1, 2, and 3, or -3, -50, -100, all that sort of stuff. And so integers is a specific set. And if you add to that then ratios of integers, we get rational numbers. Now, the word rational doesn't come from the same, where it's not used in the same sense that you say, oh, that person's irrational, they're crazy. And so rational is not crazy. In this case, the rational comes from the word ratio. Okay, so a rational number is a number that is derived from a ratio like 2/3, or 0.3. You know, 0.3 is 3/10. That 0.6 with the bar above it, that means 6 is repeated, and so that's a 0.66666 infinitely long. Now, what makes a rational number isn't necessarily the way it's notated. Okay, so 2/3 and 0.6 repeated are the same number, they're just notated differently, they're represented differently. So in a sense, all of your natural numbers, even though you didn't write 3/1 or 6/1, that's still a rational number. So when we are talking about these sets, that the rational numbers include the integers, whole numbers, and natural numbers, even though not all integers are natural numbers. Okay, so real numbers. We talk about rational numbers as being all those numbers, including natural numbers, whole numbers, and all that. And then we have irrational numbers. Now, irrational numbers are a little different in that you can't represent them as a ratio of two integers. So the examples of that are pi. You know what pi is, 3.14159. It never repeats, nor does it terminate. So it's irrational. There's no way to make a ratio out of that number. Same thing with e, and perhaps you don't know about e, or maybe you only vaguely know about it. It's another rational number. It comes up a lot. Its value is about 2.71, and it's used a lot financially in science. It is the natural base. And then most square roots that don't give you integer answers, like the square root of 4 is 2, but the square root of 2 is 1.41, and it goes on indefinitely. There's no way that it ends, there's no way that it repeats, and so it is a rational number. So between the two of those, we get the set of real numbers. So we get this set that has numbers that we can express as ratios, others that we either use a symbol for or we leave this unreduced. Now, I'm not going to have you use calculators in this class because I want you to develop, number one, a numbers sense. How much do numbers really, what do they mean? How can you accurately represent them? And so, to me, if you give me an answer as the square root of 2, that's an exact value. There's no way to put that in a calculator and get out more than 13 digits, and that's an approximation. So the square root of 2 is an exact number, and that's going to be a perfectly good, reduced, don't need it any other way kind of answer in this class. And that holds true with integer ratios. I would much rather you represent numbers as 1/2, which is just what it is, a ratio of two integers. It's exactly 1/2. 0.5, well, in a sense it's exactly 1/2, but it's not exactly the same thing because you could round to get to a 0.5. Like 0.4999 can reasonably be rounded to 0.5, but it's not exactly 0.5. But 1/2 is exactly that. So for that reason, I want you always to give me answers as integer ratios more so than decimal numbers. Now you see that funny looking R up in the upper right-hand corner. That is the symbol for a real number. And the way you read that is the set of real numbers. That's all that means. It's just a quick way to say the set of real numbers. That's not something we use in an equation or anything like that, but when we're describing things, like if you say what are the valid numbers in this function, what is the domain of this function, you can write that funny looking R because it's a complete sentence in itself, the set of, or the complete expression in itself, it's the set of real numbers. And so it's a handy one to pull out. Now the other sets of numbers like integers have similar kinds of letters, and I might slip them in occasionally, but the important one is that R. Okay, so let's talk about the number line. I think you've all seen the number line. You've all done things with the number line. And so basically what you do is you write this line, decide on a measure, and you label these things starting from 0, and you go up to the right and down to the left, increasing numbers on the right, 1, 2, 3, 4 as you go right, -1, -2, -3 as you go left. And so we call the 0 there the origin. Okay, so that's where things start. Now, the thing to remember about real numbers is that all real numbers can be put on the number line. Now you say, well, you don't know pi to an infinitely number of digits, but still, as finely as we can put it, we can put pi just right after 3 and before 4. You know, there's an exact place for it. Same thing with the square root of 2. So if you're not sure if something is a real number or not, you can always ask yourself, can I put this number on the number line? If you can, it's a real number. It's that simple of a test. So we talk about order on the number line, and what we talk about here is greater than and less than. So if we have A and B, where A is to the left of B, doesn't matter if we're talking about positive or negative numbers, but just if A is on the left, B is on the right, we say that A is less than B, or B is greater than A. Now we can also put in a less than or equal to sign in there, and that's written like that. And so we'll use those to indicate one is larger than the other, and it's always with respect to the number line. So -6 is less than -5. Even though we have the sense that a 6 is a bigger number than 5, we'll get to that kind of notion later, but -6 is less than -5 because it lies to the left on the number line. So here's a few examples of numbers. -6 is less than -1. All right, so we have a bunch of properties that we'll get into on numbers, and the first one is we'll talk about the additive inverse. Now the additive inverse is essentially the negative version of the number that we're talking about. So if with respect to the origin we have a number A, we talk about -A as being the additive inverse. And the thing about the additive inverse is that it's what you add to a number to get to 0. Also, the additive inverse of the additive inverse is the number. So in other words, a negative A is the positive A. And so when we're, as by example, if we have the number 3, the additive inverse of 3 is -3, so that equals 0. -3 equals 3. Now, the book calls it the opposite. The additive inverse is the opposite of a number. And I think you have to be really careful with that word. And in fact, I try and avoid it as much as I can, because there's a lot of ways to look at things as the opposite. And generally what happens when people use the word opposite incorrectly is that they'll talk about the reciprocal of a number as being the opposite, that the opposite of 2 is 1/2. And when you're thinking about rational expressions, ratios, fractions, and things like that, that's kind of a natural usage of the word opposite. So for me, it's just better to stay away from it. Let's be precise. Let's talk about 1/A as being the reciprocal, and let's talk about -A as being the additive inverse. Now it's a lot of syllables, and it sounds kind of technical and all that, but just get used to the notion that it's the additive inverse or the negative version of a number. Now I have this notion of the absolute value. And one way to look at the absolute value is that the absolute value gives essentially the magnitude or the size of a number. So if we talk about 5, the absolute value of 5 is just 5. The absolute value of -5 is 5. And so one way to think about this is like if I'm measuring something, I take out my tape measure and I'm going to measure this desk. If I start here, hook it, and then I look over here and I measure 48 inches, if I do it the other way around, I'll get to 48 again. And you know, we talk about the length of the table as being 48 inches. I'm not talking about positive or negative 48. I'm talking about the size of something. So we generally talk about sizes as being positive numbers. And so look at absolute value not only as the positive version of the number that you're considering, but think of it as the size of a number. So the absolute value of A is always non-negative, and that may sound like a double negative. It is, but it doesn't mean that it's positive. It could be 0 as well. So when we're trying to refer to numbers as being 0 and positive numbers, like the absolute value, we talk about them as being non-negative. So just a little clarification that non-negative includes 0 as well. Okay, so let's look at this number line again, and let's consider a notion of the distance between two real numbers. So if A is like that number line I drew earlier, where A is less than B, we talk about the distance as being the difference, B minus A, right? So if A is at 2 and B is at 5, then 5 minus 2 is the difference, is the distance between A and B. So I'll show that here. So here we have -2 and 3. And so the distance there, we take the difference, and in this case, we're going to take 3 minus the -2. Now notice the use of the parentheses there, where we say, okay, if it's B minus A, then it's going to be 3 minus whatever value that A is. In this case, it's -2. I get the double negative out of this thing, so the distance is 5. But you should be able to see fairly easily graphically that that's the case, that when you have a positive and a negative number, that the distance between the two are going to be the sum of the numbers rather than the distance. So one of the ways that we can do this to make sure that we're not, that we don't have to know which one is the larger number is we can take the absolute value of that difference, and then we get that distance. So it doesn't matter if we use the 3 first or the -2 first. If we say 3 minus a -2, we get 5, and if we say -2 minus 3, we get the absolute value of -5, which is then 5. So we get the same thing. So absolute values, I'm sure you've seen them before, but what I'd like you to think about the absolute value now is when you see the difference between two numbers, you're talking about the distance between the two. And that'll be really helpful when we get to inequalities to really understand what's going on with an inequality. Okay, so that's essentially section 1.1 in your book. And the exercises